University of Wisconsin-Madison physicists have made one of the highest performance atomic clocks ever, they announced February 16 in the journal Nature. Their instrument, known as an optical lattice atomic clock, can measure differences in time to a precision equivalent to losing just 1 second every 300 billion years, and is the first example of a multiplexed optical clock, where 6 separate clocks can exist in the same environment. Its design allows the team to test ways to search for gravitational waves, attempt to detect dark matter, and discover new physics with clocks. We're working to both improve their performance and to develop emerging applications that are enabled by this improved performance. Atomic clocks are so precise because they take advantage of a fundamental property of atoms. When an electron changes energy levels, it absorbs or emits light with a. By comparison, Kolkowitz's group has a relatively lousy laser, he says, so they knew that any clock they built would not be the most accurate or precise on its own. But they also knew that many downstream applications of optical clocks will require portable, commercially available lasers like theirs. Designing a clock that could use average lasers would be a boon. In their new study, they created a multiplexed clock, where strontium atoms can be separated into multiple clocks arranged in a line in the same vacuum chamber. However, when they shined the laser on 2 clocks in the chamber at the same time and compared them, the number of atoms with excited electrons stayed the same between the 2 clocks for up to 26 seconds. But because the clocks are in the same environment and experience the exact same laser light, the effect of the laser drops out completely. The group next asked how precisely they could measure differences between the clocks. 2 groups of atoms that are in slightly different environments will tick at slightly different rates, depending on gravity, magnetic fields, or other conditions. They ran their experiment over 1,000 times, measuring the difference in the ticking frequency of their 2 clocks for a total of around 3 hours. As expected, because the clocks were in 2 slightly different locations, the ticking was slightly different. The team demonstrated that as they took more and more measurements, they were better able to measure those differences. Ultimately, the researchers could detect a difference in ticking rate between the 2 clocks that would correspond to them disagreeing with each other by only 1 second every 300 billion years. A measurement of precision timekeeping that sets a world record for 2 spatially separated clocks. It would have also been a world record for the overall most precise frequency difference if not for another paper, published in the same issue of Nature. That study was led by a group at GILA, a research institute in Colorado. The GILA group detected a frequency difference between the top and bottom of a dispersed cloud of atoms about 10 times better than the UW-Madison group. Their results, obtained at 1 mm separation, also represent the shortest distance to date at which Einstein's theory of general relativity has been tested with clocks. That's really significant for a lot of real-world applications, where our laser looks a lot more like what you would take out into the field. To demonstrate the potential applications of their clocks, Kolkowitz's team compared the frequency changes between each pair of 6 multiplexed clocks in a. Imagine a cloud of dark matter passes through a network of clocks. Are there ways that I can see that dark matter in these comparisons? Kolkowitz asks. That's an experiment we can do now that you just couldn't do in any previous experimental system. Jung, X, Dauld, J, Lacob, V. et al. Differential clock comparisons with a multiplexed optical lattice clock. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.